Welcome everyone to today's HPL seminar. Today we'll be hearing from Meng Li. Meng is currently a master's student advised by Walter Herzog. Meng started her studies at Shenyang Sport University in China, where she received a bachelor's degree in kinesiology. She then pursued a master's degree at Beijing Sport Institute, where she focused on the relationship between bone density and hormones in female basketball athletes. Meng has also worked with the speed skating team on Team China as an assistant to their physiologist. She met Walter while the team was training at the Olympic Oval. Her research studies currently focus on the microstructure of muscle, but she is also interested in exploring the function of Botox on muscle function. Some fun facts about Meng are she used to be a belly dance coach. She likes to listen to all types of music, and she loves to eat pizza, and she welcomes any good pizza recommendations from the audience. So as a reminder, I'll first turn it over to Meng for her presentation, and then we'll have a question and answer period to follow.
Okay. Thanks for the introduction, Emily. Yeah. And now I'm just search. So can you see my screen?
Yes, looks great.
Good. Thanks for the introduction, and it's my great honor to have this talk for HPL seminar today. I'm going to today talk about the nature of Sarcomere non-uniformity in skeletal muscles. Before I start to explain the Sarcomere non-uniformity, let's go back to review the structure of muscle. So this whole muscle composed of bundles of fascicles, which are in turn composed of muscle fiber bundles. A muscle fiber is composed of smaller bundles known as these myofibrils. The myofibrils are made up of sarcomeres connected in series. Let's focus on the single sarcomeres here. A sarcomere has 6 filaments, these purple ones, which are mainly composed of myosin, making into this A band. The myosin filaments also have finger-like projections known as the cross bridges. And the thinner filaments, mainly composed of actin, extended from the dead lines and then ending within the A band. Surrounding the dead line is the region of I band. The I band is a zone of thin filaments that is not superimposed by the thick filaments. So when the muscle is activated, the actin filaments slide into the spaces between the myosin filaments. Thereby, the cross bridges interact. About the passive force within a sarcomere, it is exclusively provided by the titin. These yellow and green lines here. So these third types of the filaments represent as a spring, spans the half length of the sarcomere, running from the dead line, ending to the middle of the myosin filament. Also, when these sarcomeres connected in series, making into this myofibril, the passive force is exclusively provided by titin. For this reason, the myofibril would be a fabulous specimen for us to study the sarcomere non-uniformity. Let's go back to talk about the sarcomere non-uniformity. Literally, we can just understand the sarcomere non-uniformity as these non-uniform sarcomeres connected in series in this myofibril. If we have each of these individual sarcomeres as L1, L2, L3, L4, and L5, etc., conceptually, the sarcomere length non-uniformity can be expressed as this equation. In the past years, there has been a great advance in experiments using isolated myofibrils and the sarcomeres. This technique allows us to directly evaluate sarcomere length non-uniformity. So this is a view of isolated myofibril from the rabbit thoracic muscle, suspending with both ends fixed. Under the microscope, you can clearly observe these A bands, even the M line in the middle of the B bands, and then the dead lines locating in the middle of each I band. For giving you an idea about the thickness of this myofibril, it is usually around 1 micron, which equals to only about 1% of the human hair diameter. Besides, you may not see great non-uniform among these sarcomeres in this picture, but when we measure them carefully by some ways, there will be various lengths. I will just introduce how we measure them later in the next method part. So based on the information above, people may ask the question, why we care about the sarcomere length non-uniformity, why we want to study it, or why it is important. There are several reasons. The most important reason is because the sarcomere length non-uniformity is usually considered as a cause, the mechanism for a lot of muscle properties, like the create behavior of muscle, which is a slowly change in the muscle force for the asymmetric contraction at steady state, and the residual force depression, which can be understood as a loss of the steady state isometric force that occurs after shortening of an activated muscle. Also, for the sarcomere length non-uniformity, it is thought the cause of the residual force enhancement. So here I'm just going to show you one example, the residual force enhancement. Imagine we have a muscle which is asymmetrically activated. The length and the corresponding force will be like this gray dotted line. But when you have a muscle in a shorter length activated and then stretch it to the same length, the length will be like this red lines. Then the force after the stretch will be like this. There's a peak here, and after this muscle reaches to its steady state, there's a long, consistent, larger force than the purely isometric contraction, which we call the residual force enhancement. So what's the sarcomere length non-uniformity theory claims is like this. For example, we have purely isometric contraction muscle, and the average sarcomere length here of this descending of the force length relationship. And now the other shorter muscle is activated. The average sarcomere length will be in a higher position. Then as we stretch it to the same length as the purely isometric contraction muscle, some sarcomeres will be stretched in a short magnitude, as this blue star shown here, while other sarcomeres within this muscle will be stretched in a larger magnitude, which will be out of the descending of the force length relationship locating at this passive curve here. What the sarcomere length non-uniformity theory explained as in the end, the total force for this stretched muscle is larger for the total force of the purely isometric contraction muscle. And this was caused by these non-uniform sarcomere lengths. However, obviously, the precondition for this explanation was the sarcomeres were uniform before they were actively stretched. However, this is not the case. People actually observe the phenomena of the sarcomere length non-uniformity at any conditions of muscle, like in the passive and active states. Despite those explanations for the crate behavior, the residual force enhancement or the residual force depression are correct or not, we realize some facts that making us have strong motivations to explore the Sarcomere length non-uniformity. First, we found this phenomenon was observed at all structure level, from the individual myofibrils to the fiber, the muscle tendon unit, or even the whole muscle in vivo. And we also realized that it is important to help us uncover some functions of the skeletal muscle. The last, we just know little about the features of the Sarcomere non-uniformity, even simply in the passive conditions, the active conditions, and from the passive to the active conditions. Therefore, our objective is to quantify the Sarcomere length non-uniformities in active and passive skeletal myofibrils. There are three hypotheses based on the objective. First, the hypothesis that the passive sarcomere always go to the same lengths in the passive conditions, and the active sarcomeres always go to the same lengths in the active conditions. And finally, the hypothesis that the sarcomere length non-uniformity becomes greater from the passive to the active conditions. About the methods, as this schematic shows the total myofibril length or the mean sarcomere length remain unchanged. We did 3 activation, deactivation cycles. Here in the yellow lines, you see when the myofibril is relaxed, and here you see the red lines that the myofibril is activated. Totally, the myofibril was activated and deactivated 3 times. And then we measured the sarcomere length at 7 different instances during this protocol. We measured it here, what I call O, the initial relaxed state prior to any activations. And then we measured this A1. A stands for the activation 1. So we measure it and when the muscle myofibril is activated at the first time. And we have R1, R2, which are the sarcomere length measurement when the muscle was in the passive state after the first activation and the second activation cycle. And then we have A2, A3, which are the sarcomere length measurement in the second and the third activation, when the muscle is activated at the second and the third time. We did those 3 activation, deactivation cycles. So the protocol I just show you here, we did that 3 average sarcomere lengths. One of those is 2.7 microns, second is 3.2 microns, and the third is 3.6 microns. The reason why we did this is because we want to do at the short sarcomere length, 2.7 microns, where there's almost no passive force here. And at 3.2 microns, there is a little bit passive force. But at 3.6 microns, where we expect that in this system, the passive force is similar or even slightly higher compared to the active force. Now I'm showing you a movie where we activate the myofibril. So here is the myofibril in the passive state. When this myofibril is activated like this, you may hard to see, or maybe if you focus on the left hand of here, then you see that the sarcomeres are shortening, and they tend to be elongate at some parts on the right hand. So again, And here you are in the active state, and then we deactivate it. What you will see is essentially the sarcomeres tend to go back to their original configuration, what they have, like this. So after the experiments, each of the record videos were imported into the MATLAB. We wrote the program which can recognize the A bands and the I bands by different intensity. Then an intensity curve was produced like this blue line shown here. And with the detected A band edges, the center of each A band was calculated. And finally, the circumferences will be calculated at the difference of this adjacent center of the A bands. Then in the results, what I'm going to show you is first, I will show you the sarcomere length non-uniformity across the 7 states, the 4 relaxed states, the 3 active states. And then secondly, I will compare the sarcomere lengths in the passive states, O, R1, R2, and R3. We want to see if sarcomere lengths are randomly going to the different places all the time, or if they would just return to about the same length in all passive states. Then I will show you the results where we compare the active states that I'm calling A1, A2, and A3. And again, I want to compare the sarcomere lengths in A1, A2, and A3 and see if the sarcomere lengths or if they are all different or the same. Then I will show the how sarcomere lengths compare from the passive to the active state. As you saw in the myofibril, what I just showed you that the activating UV, it seems the sarcomere lengths tend to get different. I just want to compare them to see if the sarcomere lengths somehow correspond. And finally, so here in the first 3 parts, I just show the sarcomere length is the absolute value. But in the last part, I'd like to show you is how sarcomere lengths change, the elongations or the shortenings of the sarcomere lengths during the activations. So this will be the changing of the lengths again, instead of the absolute value. Now I'm going to start the first part, sarcomere length non-uniformities. There were several ways for us to quantify these sarcomere length non-uniformities, like the coefficient of variation, the absolute variance, etc. Here, I'm just going to show you the sarcomere length non-uniformity in terms of the standard deviation at the vertical axis by microns. And here the x-axis represents each state. So in the passive state conditions as shown in this small schematic on the right hand, the O, R1, R2, and R3, the sarcomere length non-uniformity is shown as like this. You can see they were, for each group, the sarcomere length non-uniformity slightly increased at the times of the activation, deactivation cycles increasing. As shown, and continuously upon activation, the sarcomere length non-uniformity substantially became higher compared to the passive states. These are the relate to the sarcomeres here, the A1, A2, and A3. And besides, longitudinally, you can also observe the increasing tendency as the sarcomeres become longer, both in the active and the passive states. For this part of the result, what I'd like you to take from the slide is that the sarcomere length non-uniformities measured at the standard deviation are slightly greater in all the active states compared to the passive states. And in the next following part, we answer the question, do Sarcomere lenses evolve randomly each time when they are deactivated? Then we have the results for showing the Sarcomere lens non-uniformity from the passive to the passive state. As shown in the figure, now we are going to compare the Sarcomere lenses of the first passive state O to the second one, R1. And continuously the R2 and R3. So on this last figure, when you are looking at the Sarcomere lenses, essentially, do they go back to the same length after the first deactivation cycle? Both axes show the individual Sarcomere lenses of O and R1. And these red scatters are the Sarcomeres in the short group. With nearly no passive force with average Sarcomere around 2.7 microns. And blue squares are the middle group Sarcomeres and the long groups. A best fitting line was made by forcing the intercept at 0, so that the slope of this line is pretty close to 1. With a higher R-square value, which means that when the Sarcomere has a length at O state, they went back to the essentially the same length. And since the reliability in this study is 0.2 microns, we also have two dotted lines on either side of the best fitting line. In order to establish this reliability band, I took some samples, analyzed them 3 times on 3 different days. And the reliability of this measurement was plus and minus 0.2 microns. So that in this band, for all the practical purposes, Sarcomeres within this reliability band, for us, that means they are exactly the same between the O and the R1 states. Because, they could be very just purely due to the reliability. So now if you see how we look these results from the O2 to R2 state after the second activation, again, we have a slope essentially very close to 1 and with a higher R-square value, the same result as before. For the third one, compare the initial state of the third activation-deactivation cycle. We got the same slope with similar higher R-square value. All the figures indicate that as the result shown, that the Sarcomeres tend to go back to the same length that we had at the beginning. After they experience the activation-deactivation cycles, then we have the results for showing the Sarcomere length non-uniformities from active to the active states. Answering the question, do Sarcomeres evolve randomly each time upon activation? And we produced similar figures by the same way to observe the Sarcomere length non-uniformities upon activation. The axis represents the Sarcomere length in A1, relates to the right figure, the A1 here, and the Y represents the Sarcomeres in A2 here. Generally, like the previous figure showed, the active Sarcomeres became more distributed. Even like this, we still got the slope very close to 1. Also with a high coefficient of determination, which is 0.84. Likewise, very similar results were found by observing the Sarcomere lenses upon first activation versus the third activation. Then we can just understand the result, like although more members of the sarcomeres become shorter or longer upon activations, there's still the same tendency were found that the sarcomeres tend to stay at the similar lengths upon activations. As follows, we have the results for showing the sarcomere length non-uniformity from passive to the active state. So again, as shown in this small schematic on the right in this figure, it shows the sarcomere changes from the O to A1, the neighboring state, when the methyl is activated. So how the sarcomere length change? The horizontal axis is the initial sarcomere length is O, and the y-axis is the sarcomere length is A1. For this fast fitting line, we got the slope over 1 with a negative intercept of minus 1.14. The relatively lower R-square value means a relatively weak correlation between the sarcomere lengths of O versus A1. In another way, if we force the intercept at 0, there will be a big loss of accuracy by showing a slope over than 1, demonstrating that there may be different mechanisms controlling the sarcomere lengths in the passive and active states, respectively. Here, if we added an identify, like the yellow dotted line in this figure, which we say y equals x. If a sarcomere length keeps the same from the passive to this active state, it will fall exactly on this identity line. But you can see clearly that for most of these sarcomeres, this is not the case. From the beginning, for the very short lengths around 2.5 or 2.7 microns, most sarcomeres tend to fall below this identity line. As the sarcomeres become longer, for this green long sarcomeres, many of them fall above this yellow line. To be more specific, if we mark we make y equals x, combining with the equation of the back fitting line, we will get an average sarcomere length of 3.4 microns. What indicates here is that when sarcomeres tend to be short in the relaxed state, they tend to become shorter. When they're long at the beginning, they tend to become longer, which means that upon the activations for the sarcomere lengths around 3.4, as shown in the last figure here, they were quite stable, almost no length changes during the activation. And here for the next passage to the active phase, R1 to A2, we got the similar result with a slope over 1 and the negative intercept and relatively weak relationship. Also for the R2 to R3, we got the similar result as well. What I want to point out here is that these regression lines are clearly not with a slope of 1 and cannot be forced through 0. At the same phenomena occurring from the passive to the active state are clearly not the same. So to re-emphasize the result for this part, when the myofibril was activated, we want to find that the short sarcomeres tend to remain short and the long sarcomeres tend to remain long. So we have these length changes now upon activation. And so far, I only show you the sarcomere lengths. But now I want to show that the changes of the length that occurs in the first activation cycle, the second and the third activation cycle. These are different graphs from the before. So here we have the length changes from 0 state to the first activation on the horizontal axis, which calculated by the secondary length A1 minus O. And the length change is measured from the relaxed state to the first activation state. And we have the second length change in the second cycle from the initial state to A2, which calculated by the second length in A2 minus O. So here we see that the large proportion of the sarcomeres are in this third quadrant. What that means is that when the sarcomeres tended to become shorter in the first activation cycle, then it tended to become shorter in the second activation cycle as well. And then you now look at the sarcomeres that are elongated in the first activation cycle. They tend to elongate at the second activation cycle as well. So by far, at the majority of the sarcomeres lead that when they shorten, they tend to shorten in the subsequent cycle. When they elongated in the first cycle, they tend to elongate in the second cycle and the third cycle as well. There were also a few sarcomeres that they didn't follow that pattern. But when you look at the reliability lines here, what I'm talking about the 4 or 5 on the top quadrant, there's only 1. Also on the fourth quadrant, there are only around 5 or 4 didn't follow that pattern. All the other ones follow the pattern or within the range of the reliability band. So really, sarcomeres tend to elongate it at the first cycle. They tend to elongate it as well in the subsequent cycle and vice versa. So here, let me just summarize the results. The first, the passive sarcomeres tend to stay at the similar lengths, and the active sarcomeres tend to stay at the similar lengths too. From the passive to the active state, the short sarcomeres tend to remain short, the long sarcomeres remain long, and the sarcomere length changes upon activation tend to also remain the same. Based on those results, we proposed several possible mechanisms on sarcomere length non-uniformities. Overall, we suppose, along with the myofibril, different diameters of the sarcomeres making different numbers of proteins in each sarcomere. So in the passive state, we proposed several possibilities for the sarcomere length non-uniformities. The sarcomere length non-uniformities virtually could be caused by the different numbers of titin. Or even if we were not sure the numbers of the titin are same or not, the various lengths of the titin isoform can produce diverse forces. Since this experiment was conducted in the rabbit muscle, it is known that there are 2 types of stiffness segment on the titin, a stiff one and a soft one. If one sarcomere has stiff titin, it would tend to keep the short length within a with a relatively thick diameter, and the others with this soft titin, they would be longer and thinner. For this reason, the sarcomere length may shorten the non-uniform lengths. And in the active condition, these different diameter sarcomeres containing different numbers of contractile proteins will produce different active force. Or we say that the sarcomeres with various diameters on different capacity to produce active forces. Again, in this picture, we are working on the descending limb of the first length relationship. Well, from the passive to the active state, what will dominate that particular behavior? It will make sense that the shorter ones that have more overlap rate that are higher at the descending mean. These ones will tend to get shorter because the higher reliability, the higher overlap rate. And for this long sarcomeres, they have relatively lower overlap with lower active force, and then they tend to become longer. Except for all those reasons, there's another possibility that the titan may behave differently upon activation. There were studies speculating that the PVK segment in the titan can interact with the actin filament. So during the state of activation, the PVK segment on some titan may attach to the actin, while these neighboring ones are still free. By this way, the sarcomeres present various lengths. So finally, we suspect that the sarcomere length non-uniformities could be the result of the inner equilibrium for each sarcomere. So the messages we want you to take the first, the sarcomere length non-uniformities are not occurring randomly, but can be predicted. And the passive sarcomere length non-uniformities are likely due to the different numbers of titan and the different stiffness of titan in seriously arranged sarcomeres. And for the active conditions, the sarcomere length non-uniformities can be caused by the passive long sarcomeres become longer and the passive short sarcomeres become shorter. So the dispersion may be caused by the different amounts of contractile proteins between the sarcomeres and the properties of the descending length of the force length relationship. And finally, thanks my supervisor, Walter Herzog, and thanks for Kim Leonard, telling me the lab, and thanks for Linus, Wang, Anquan, and other people in our group.
Thank you, Meng. Great. At this time, I'd kindly ask the audience members that if you're comfortable to please turn on your Zoom camera to allow for a better discussion. You can use the raised hand function on Zoom to ask your question or type it in the chat box and I'll read it aloud. So Amin, please get us started.
Thank you, Meng, for your presentation. I really enjoyed it. One result that I was waiting for you to present was about force. So you have the contraction force, so you can read it from the device that you have, right? And that force theoretically should be equal to the summation of active and passive force for each sarcomere. Do you agree with that?
Yeah, we didn't, that's a good question. We actually didn't measure the force in this experiment, since we suspect within each sarcomere or within the myofibril, the force for each sarcomere was suspectly the same. Then the total force. So that may not super important for the sarcomere length non-uniformity. We didn't measure the individual titan force or the active force. We just simply observe the sarcomere length non-uniformity. Measure the sarcomere length.
Because you have the initial length and like final length of the sarcomere, and you have the like passive and active curve. So at this, I think you can calculate the total force generated by the sarcomere during the activation. For each sarcomere, you can calculate that force, and you can just somehow like validate your result to see if all those forces are equal, or maybe you get some maybe variation in the force, and then there's like another factor maybe there that you miss. So that could be something you can study.
Yeah, that may be something related to the physical properties, since we think along with the myofibril, at each point the force should be the same.
Yeah.
So we can just simply measure the force within at the end of the myofibril. That's actually equal to the force for each sarcomere.
Mm-hmm. Yeah.
Yes.
John, please go ahead.
My question might be very similar to Amin's. So in a series of sarcomeres, the force has to be equal on each sarcomere. And so your explanation using the length tension curve of why some get longer and some get shorter doesn't seem to make sense, because you don't have a constant force across those three.
Yeah, what I explained to that was the sarcomere length non-uniformity. Until now, we proved that the theory was not correct, since at each one the force should be the same, the total force should be the same.
Yeah, okay, thanks.
Michael, go ahead.
Thanks, Meng. Interesting presentation. I was wondering if you could comment on how much of your results are due to the experimental setup. So you get the shortest sarcomere lengths, I think, near the fixed end of the contraption. And if both ends were able to freely move, would you see the same non-uniformity, or would you have more uniformity?
Yeah, except for the reliability units that due to my operation, I suspect that we have the needle on the left side of the myofibril, and we typically people measure the force by the cantilever, and then they calculate the force by the differences of the two different position of these two cantilevers. But in this experiment, since we didn't have that technique to have both ends for the very stiff needle, so I just did these two pairs of the cantilever together to make them as stiff as they can, so that we can get as much as the purely isometric force as we can. So I would say when we given the solutions, we have very slight operation. So even though that sometimes due to the system setting, the needle drifting a little bit, but that may not cause a very big difference. Sarcomere length fluctuate. So I would, at least for this system setting, I would expect they can, the sarcomere length is as much as much as we can to make them like they were at the actual situation. Yeah.
Okay, thank you. I have one more question if no one else has a question. Do you have like you have all these scatter plots with nice correlations, but I was wondering if you had like a measure of error for each of the individual data points, like a root mean squared error or something. And the only reason I ask is that when you show the plot with the like A1 versus resting state, A2 versus resting state, it seems like there's a lot of points that start, let's say at 0.5 change in the first, between the first state and the resting state. And then in the next ones, they get a little bigger, like they now become 1.5 difference from the resting state. I was wondering if you could comment on that.
I'm sorry, I can't give you give you an exact answer for that, but I suspect that we in that part of the result, we didn't track the individual sarcomeres. So that result was shown at the sarcomere length changes may have a better results for showing your questions like the magnitudes are different by several cycles of activation, deactivation cycle. Am I understand your question correctly?
I think so. Like so each data point on your scatter plots represents the length of one single sarcomere in each of the two conditions, right?
In the results, as you mentioned, from the passive to active, that may not. But for the last part of the result, the sarcomere changes, the four quadrants, that's the individual sarcomeres tracking.
Okay, I guess I'm trying to understand because at the beginning when you had these bar graphs or these box plots, I can't remember, you show that like the standard deviations of the sarcomere lengths get larger and larger as the active states go on, but then the data looks very similar when you show the scatter plots. So I guess I'm just wondering where the difference is coming from between those two measures.
Oh, yeah, that's a good question. Sorry, I think I don't have an exact answer for that now. Yeah,
Oh,
I was
okay.
just thinking about it. Yeah,
Okay. Thank you.
Mm-hmm.
Sangwon?
Hey, Meng, and thank you, Emily. So I have a more question about the methodology that you did your experiments. So you showed a video where you have a needle and a myofibril here, and then you have a pair of cantilever at the end. And then in order to make this whole system as stiff as possible, you seem to wrap the cantilevers into as a one. You wrap the cantilever with the myofibril. So to me, in this case, it's hard to see if the myofibril is fully deactivated or not. So if you are saying you are comparing the sarcomere length between when you repeat activation and deactivation, how do you know it was fully deactivated?
That's really a nice question. I would say between each step, between each activation, deactivation cycle, we may not do that. But the thing, what I can do is that at the end of the experiment, when I move the myofibril or the needle suddenly a long way to close, make them the two ends closer. If the myofibril was not fully deactivated, the sarcomeres will become. You will see the A band was shortening in the big magnitude, and there's no curve along with the myofibril. That means they were still not fully deactivated. But the myofibril is fully deactivated, they will score like this. They will curve on that. Yeah.
Walter, go ahead.
Thanks. Nice presentation, Meng. I have a couple of questions. You know, you mentioned one possibility for why you might have different sarcomere lengths in the active and or the passive state is because the sarcomeres that are in series might have a different diameter, they might have a different cross-sectional area, and therefore might have different amounts of tightening, different amounts of contractile proteins acting in myosin. When you look at the myofibril, do you think that's actually correct? Can you see that different sarcomeres in the same myofibril have a different thickness, or have you tried to measure along one myofibril the diameter and see if you find differences?
by eyes under the microscope, it's hard to differentiate the thickness of the myofibril. And also in the math lab, I try to measure this since the operation reliability is around 0.2 microns. Sometimes it's hard to say that the thickness, the measurement of the thickness is correct or not. But I saw some references. They show the fibers or the whole muscle in an electron microscope. I found some people observe the different diameters for the sarcomeres.
So you could not see it in your machinery, but you think that there is evidence out there that sarcomeres in a myofibril can have different thicknesses.
Yeah, I think that is it.
So, this was done on a rabbit, and every muscle in, I guess, in frogs and mammalian muscles that I've looked at, we always see these sarcomere lengths non-uniformities. But when I look at the flight muscle from flies, indirect flight muscle from Drosophila, it seems to have incredibly uniform sarcomeres, at least by eye. I've never really measured them, but when you see those, they seem to be very, very uniform. Why do you think that might be? That, let's assume I'm correct, so that some muscles are very, very uniform. Why do you think that might be that, human muscles are non-uniform and indirect flight muscles of Drosophila seem to be perfectly uniform in terms of sarcomere lengths?
Yeah, that's a very popular question, I guess. People always ask, what's the real function or what's the applicable function for the sarcomere length non-uniformity these days? From my point of view, I suspect that in human or in the animals, the sarcomere length non-uniformity exists for the potential function of muscle. That means if a muscle has a phenomena of the sarcomere length non-uniformity, it will have more potential ability to produce forces. It's more flexible, or saying it has a big range for the muscle to produce the force.
Do you know of a simple function that might be different in human or mammalian skeletal muscle compared to a flight muscle in a fly? Do you know anything about that, or?
I'm not super sure about it.
Yeah. Well, one thing that strikes in human muscles, we can go through very large ranges of motion. I'm trying to flex my elbow and extend it, and so we go through very big sarcomere length changes. Whereas I have read that in Drosophila, that the length changes of the sarcomeres when the animal is flying, when the fruit fly is flying, is somewhere between 3 and 5%. So it only needs a very small range, and it's also very, very, very stiff compared to human muscle, which is very soft. I can easily move my elbows through the range of motion, and I don't really encounter any passive forces. So I assume in Drosophila, you might have much more structural proteins that give a sarcomere this stiffness. And so maybe the stiffness is inversely related to the excursion that you need. And if you don't need a lot of excursion, you make it stiff. And if you need a lot of excursion, you don't want it to be stiff, because, in children with cerebral palsy that have stiff muscles, that really affects, their movement patterns and what they can do. I'm going to stop here. I might have a couple more questions, but I see that other hands are up, so I'm going to stop for a moment.
Rob, please go ahead.
Meng, I'm wondering, when you take your measurement of sarcomere length at rest between the 3 different active contractions. I'm wondering if the time since the end of the contraction matters, and have you tried to just, at the end of a contraction, measure the sarcomere length, say at the end of those things, just keep going and measure it at 1 second or 2 seconds or a minute or 2 minutes? Because I guess what I'm wondering is, does the Titan tertiary structure take a certain time constant to sort of rebuild and put things back into shape? And so that the time after the end of the contraction might be important as to what the final outcome is. I remember seeing one of Tim Leonard's contractions in the same sort of prep, and at very long length, if he took, I might be misinterpreting you, Tim, but at very long length, when you brought it back over a long length of time, you'd see it all sort of fold back together again and look nice and tidy. So I'm wondering have you looked at the time constant of recovery?
I guess I like your questions. That's a question I had before when I conducted experiments. I discussed with Walter and I checked some papers. I suppose what you potentially want to ask is the IG domains maybe fold or unfold. They need time to unfolding, and that's I would say I didn't exactly measure the length change minute by minute, but what I did was between each cycle I wait for 10 minutes and then measure the and then activate the myofibril again. Since there's reference mentioned that the Titan may be mechanically fatigued, or the Titan curve maybe move a little bit after if you just simply activated or deactivated in a short time. And yeah, since we want to exclude that cause, the mechanically fatigue or the IG domains need to time to fold or to unfold, then we just wait 10 minutes. And at the end of the 10 minutes, I did the second activation and the third activation.
Yeah.
So sorry, Rob, can I make a comment here? Because I'm not sure, I don't think Ziad is on the call here, but Ziad and then Kwan did exactly that study. So they looked at activating a muscle in their case. So they activated the tibialis anterior of a mouse, and then they used second harmonic generation to identify individual sarcomere lengths in an entire muscle. So a very different preparation, an entire muscle, but they could identify a myofibril and, I don't know, 30 to 50 sarcomeres in series. And then they looked at it at 1 second, 2 seconds, 3 seconds. And what they found is that from the passive to the active state, exactly the same as Meng, there would be a great dispersion of the sarcomere, so greater non-uniformity in the active state compared to passive. But when they followed it, so they followed it, the non-uniformity was greatest right at the beginning when they had fully activated. And then over time, it was not very long, it was about 8 seconds. But then over these 8 seconds, I think it was, every second, the sarcomere length uniformity then seemed to get slightly more uniform. So it almost seemed when you activated it, you kind of blew it all up and it went high wire and was very non-uniform. And then it came slowly back over that time frame to more uniform and seemed to continue doing so. So if he could have measured longer, might even become more uniform over time. So it seems to change. I guess that's the crux of the thing over time.
What's the mechanism you think might be contributing to that change?
Well,
you tell me. It's Meng's seminar, so she'll answer that question.
I suppose that's because the some segment of the type along with the titan need time to recover. They just cover slowly, like fold it, like the idle don't need time to fold.
Okay, thank you, Meng.
Venus, please go ahead.
Yeah, hi, Mom. Very nice seminar. Thank you.
Okay.
So you mentioned in your introduction residual force enhancement and the active stretch. So did you try to stretch your myofibrils at all?
In my experiment, I didn't do that.
So if you were to speculate about the behavior of the sarcomeres, because you're saying, so the short sarcomeres, they would stay short after activation, and the long, they would stay long. So what's the behavior of the myofibrils? What would it be if you were to stretch them? The long ones and the short ones. Do you have any idea?
I have no idea about that, but I speculate that when you stretch it, activate and stretch the myofibril, the sarcomere length non-uniformity become greater, since that titan would dominate the sarcomere, the force, the passive force. I mean, there will be more passive force in the longer sarcomeres. And what we suspect the sarcomere length non-uniformity in the long sarcomeres, it is caused by the passive structure titan. And also, if I remember correctly, there are some papers did that similar experiment that they found that during active stress, the sarcomere length non-uniformity become greater than the purely isometric contraction.
Okay. So you agree that some sarcomeres would become longer, but instead of going to a length where the force is supported by by titan, when titan is not stiff, so you believe that the long ones would be supported by titan, but a stiffer titan.
I think I have the reverse answer. The long ones maybe have softer titan, and since the titan is softer and they were easily stretched, and so the long sarcomeres with softer titan maybe easily get longer when they were stretched.
Yeah,
That's
okay.
my understanding. Yeah.
Okay, thank you.
Can I just maybe add a comment there, because as Meng was indicating, we had done experiments like that where we compared non-uniformities in an isometric contraction, and then after the muscle was actively stretched to that same length, and the non-uniformities, quantified as a variance or a range or a standard deviation, seemed to be about the same. But what was really interesting, and Kwan did that work, what was really interesting was that in the isometric contraction, the sarcomere lengths seemed to continuously change. So some got shorter and some got a little bit longer, and so. Whereas after the stretch at the same length in the same myofibril, the sarcomeres seemed to be much more steady. He just quantified the slope of the length change over time. And so the slope in these individual sarcomeres was essentially zero after an active stretch, but was essentially usually not zero, shortening or lengthening. And so the long ones tended to get a little bit shorter, and the short ones tended to get a little bit longer. So there was variation there. So it seemed that after the stretch, somehow the length of the sarcomeres was much more stable than in an isometric contraction at the same length. Again, nobody asked me, please, why that is.
Go ahead, Rob.
A thought just occurred to me. When we have the traditional sarcomere length tension curves, they are of necessity the average sarcomere length tension curve. Is it possible, and has anybody measured, is the myosin length just ever so much variable from sarcomere to sarcomere? And so one sarcomere is optimal at 2.1 and one sarcomere is optimal at 2.05, or has anyone looked to see if the myosins vary from one sarcomere to the next that might correlate with these? You know, each sarcomere, you say it's longer, but maybe it's actually more optimal.
I don't have the exact answer for that. But as far as I know, the myosin filament length, the length of the myosin filament length is the same, like the 0.7 microns among all species. That's the same, but I remember their paper mentioned that the myosin can be at the stress monitor or sensor when they tap during the residual force enhancement, or sorry, I can't remember correctly, but I remember the myosin length can be changed a little bit, like 0.1 or 0.2 microns during the activity.
Is there enough resolution to see a difference, do you think? I suppose in those graphs, in those images, you're pushing the microscope a long way. Maybe it's too difficult to look at the individual myosins from one to the other. I haven't done it.
In our system, at least for the system in my experiments, we may not. But yeah, maybe what I expect was it may be more possible that the numbers of the myosin filaments in parallel may be different instead of the yes, like in one sarcomere there were 6 myosin filaments with parallel, and in their neighbor one there could be 7 or 8, something like that, instead of the length difference.
Yeah. Okay. Thank you.
So Rob, you know, and Venus can talk to that better than I because she's done those studies, but X-ray diffraction studies would suggest that in a given species, myosin length is very, very, very well controlled. So you have, you know, every 14.3 nanometer, you have a cross bridge and 60 degrees offset from the previous one. And then you have a fixed number of cross bridges per myosin, let's say in human skeletal muscle, and all mammalians seem to be, as far as I know, about the same. But then, of course, you have different species where you have very different myosin lengths. But myosin lengths, you know, from passive to fully active, elongates by about, you know, 0.02 to 0.05%. So even when you have different forces acting on it, the length change of the myosin is minute. You know, it's 1600, roughly 1600 nanometers, and then you know it goes maybe to 1605 nanometers when it's fully activated. So a fraction of a percent. So it's fairly well controlled.
But I think that the measurements of myosin length are the average. I remember Oh, there's considerable difficulty to make sure that you're sectioned right through the whole thing. And so they tend to take an average figure. But from memory, there's about 14 different variations on myosin, including embryonic myosins. And so when you damage a sarcomere, the first myosin that's produced is not the same as adult type myosin.
Yeah, that's true. And that's the same for actin. And in fact, actin is associated with a very distinct length change from the embryonic to the final state, a very substantial one that has been well documented. So for example, in frog, the actin, is as long as 1.15 or 1.2 in the embryonic state, and then goes to 0.95, 0.97. So a dramatic change in length, but that has not been reported for myosin in terms of the length. Yeah.
I'm just wondering, not reported, I agree. I'm just wondering whether it's been investigated from sarcomere to sarcomere.
Yeah, I'm not aware that somebody has looked at one sarcomere and the next one and the next one. Yeah. So, yeah. I have another question if nobody else. So, Meng, you have, as somebody mentioned, you have an active force length curve, and then you have a passive force length curve. I think it was Amin at the very beginning. And then theoretically speaking, you add the two curves up, and that gives you the total force as a function of length. And that total curve on the descending limb where you work, goes down and then has a minimum, and then it goes up again. And so now you have 20 sarcomeres in your myofibril, and they are all at a different length, which means that they are at theoretical forces that are not the same. But at the same time, this system is in series, and you could put a force transducer in between any two sarcomeres, and you would have to measure the same force. So how do you explain that? That you have these sarcomeres that are theoretically speaking at very different force levels, but somehow they seem to be in force equilibrium.
Thanks for asking the question I tried to ask.
So if I understand your question correctly, you're asking me that on the descending length, the force length relationship with the sarcomere length, the sarcomeres in different lengths, and they are in the different position of the.
So one sarcomere is here, and the force is, the force is here. Another one is there, and theoretically the force should be there. Mm-hmm. And then the other one is here, the force should be lower, and another one is there, and the force should be higher. So you get this, mm-hmm. curve that is not constant. And we know from, you have these sarcomere lengths and uniformities, we know that they are all over the place. They are about, 0.8 microns apart. So they're clearly at places where theoretically speaking, they should not have the same force. Would you have an explanation why they potentially might have the same force?
I think that largely because of the passive. On the curve, it only shows that's the active force. But
yeah, no, I'm talking about the total force. The total force is also not constant over, 0.6 or 0.8 microns of the variation that you have in sarcomere lengths and the descending limb. Even the total force, the total force is not adding up to a straight horizontal line. I mean, I don't know the answer either, but maybe if you think about the fact that the short sarcomeres tend to shorten and the long sarcomeres tend to lengthen, might that potentially give you at least a hint of a possible?
Yeah, I would say I don't have the answer for that. But
let me help a bit. At the beginning you talked about non-uniformity might be associated with force depression and force enhancement.
Yeah.
So which sarcomeres would you think would tend to get weaker if they shorten or lengthen, and which ones would you think get stronger based on the force enhancement, force depression theory?
Oh yeah, that remind me that the previous slide I showed so for the elongated sarcomere there would be the force enhancement. I think they were weaker and they have lower total force. It could be there would be lower total force, and there would be the residual force enhancement and making the force balance. And for the shorter ones, there would be the force depression, and so that the total force for these longer or shorter sarcomeres the same.
Yeah. And Dr. Leonard in 2010 showed that not only that, but in a single sarcomere, when he stretched single sarcomeres, the force enhancement was absolutely amazing. It was amazingly big for some reason, much bigger than what you would expect in a muscle for a similar stretch. So the sarcomeres seem to be very, very, very sensitive in increasing their force when they get stretched and decreasing the force when they are shortened. And then keep that force after they have been stretched or shortened, where they are much lower than you would expect isometrically or much higher than you would expect isometrically. So that force length relationship, that theoretical one plus the passive force, seems to completely fall. It seems to be completely invalid as soon as you have lengthening and shortening of sarcomeres, in the myofibril at least.
Or can we understand like the total force for the sarcomeres along within a myofibril? If their differences for the total force can reach up to 30 or 40%.
Thanks.
Other questions from the audience? Great. Please join me in thanking Meng for her presentation today, and thank you to the audience members for their questions and feedback. I hope to see everyone again next week. We'll be hearing from John Bertram, and the title of his presentation is Surprising Similarities and Differences Between Walking and Running that help explain why these gaits are effective.